Okay, fine, good. So, last week we saw the part of the gauge group. Last class, not last week, right? And so today, and then what did I write? Any questions from the last class? Nothing. Okay, good. So what we continue by writing what is standard model Lagrangian. So the way the standard model Lagrangian, the real Lagrangian is quite complicated. Okay, what you find on t-shirts is not the real Lagrangian. Okay? That is a very specific Lagrangian, which is what we will also start with, which is called classical unbroken. It's- So when I say classical, here what we means by classical means we are not aware of the quantum language. We are not aware about the quantum level. We are not okay. So if you have to write a quantum Lagrangian, you have to write the basic terms or the quantum terms. Okay. So it is quite complicated. I will write it next week. So today we'll just write the classical Lagrangian. And second part is unbroken phase. Now, in the broken phase, the Lagrangian is quite huge. Okay. If you want to look at how many pages it runs to, I would suggest we heard of this guy's name. Anybody? Weltman? What about? Yes. So this guy is this guy's supervisor, Weltman. So Martinez, and he has a fantastic book. Both of them got the Nobel Prize today. Okay. So Weltman has a fantastic book called Diagram. The very thin book where he writes the entire literature. Okay, pages and pages and pages. Okay, have a look at it. Okay, so it's a very good book, and he discusses many things very nicely. Very simplified and a very crash course on quantum level part of the Lagrangian. Okay, so when you write in the Higgs, when I say unbroken phase, what I mean is that you know it's from Ligma's cosinus unknown, what is spontaneous emission breaking. So, so I'll write the Lagrangian without SSB. So I'll write it. So this case. So it makes life easier for us, and then we'll make it complicated later, a little bit. So
Sorry, in the last class, you wrote the Higgs phase, the unbroken phase is H plus and H zero. Why do you write H plus and H zero?
okay. So why the Higgs representation is now Higgs we start with we have to give a representation. It's a complex scalar which transforms as SU2 doublet. Okay, so it is 1, 2, 1. So the T3 values in SU2 always go down. So as we go along the multiplier, the T3 values reduce by 1. So that's the reason if I want to, you can give it the same thing with H0, H minus also. You can start with this kind of notation. So, but okay. For the present, let me do this. Okay. Now in SU2, there are no complex representations. The real and complex representations are same, equal to each other. And in SU2, these are called pseudo-real representations because there is no basis in which you can show that all the sigma matrices are real. In any basis, they cannot show them to be real. So these are all pseudo real. Now, what we want is to break the Higgs break the pseudo-symmetric spontaneously. We want a scalar field which transforms exactly under a doublet, and it also has a hyperchain. Okay. Now, when you give it a doublet, it's a complex doublet, so that it has real, imaginary, real, plus imaginary. So you have four real fields. So you have four real fields, and in turn, it turns out that three of these fields will become Goldstone groups, and you will be left with one scalar field, which is not complex. It is 1 degree of freedom. And that's the reason why you have only why we want to give it in this particular presentation. So when it's spontaneously broken, so, so this will become a Goldstone boson. This will become a Goldstone boson, and this will become Higgs plus V by 2 plus I. So each of them will become a Goldstone boson, and this will become the Higgs, which is the standard model. V is the constant. So that's the reason in the unbroken phase we start with the entire thing, and we keep track of these Goldstone modes because it turns out when you're in non-abelian gauge theories, um, these play an important role in quantum correction. So if you don't take off the quantum corrections, including the Goldstone modes, um, especially in spontaneously broken things, what happens is you cannot show the gauge independence. So if you take one simple quantum correction, I'll discuss more about it later on. Say, for example, let's take some process, say, for example, some penguin, say, like this, some W is going on, some fermion going to another fermion, with other fermions up at fermions. Now, this diagram, if you compute it without Goldstone mode contribution. So here, let's take a specific process like V to S gamma. The simplest thing, you can do it in boxes and other things. Now, this process will also have the longitudinal modes of turbulence, which are the gauge dependent part, coupling like this. And this diagram has to be taken into account when computing the loop, otherwise, you cannot show that it's gauge dependent. In the history of the standard model, if you work in unitary gauge means setting all these things to the zero. It's very hard to show Reynolds. Okay, physical answers are same in any gauge, but in general, it's very hard to show Reynolds. For example, Weinberg claims that he couldn't show the reversibility of standard model because he was always working on unitary gauge. The RZ gauges in which these things are present, which are non-zero. So in the RZ gauge, they all come with something called a Xi pattern. Okay, and the gauge part also will come with the Xi pattern. Okay, the longitudinal modes. And you can take Xi to be any number, and you can show the Xi part in X. So these diagrams. So it's not trivial that the root level. I'll mention it in the next class when I discuss standard. Renormability itself does not depend on gauge. Manifestly to show the renormability, that depends, that makes life easier in our case. The actual process of renormability or the physical observables is not depend are not gauge. In the unitary gauge, yeah, it seems it's not renormable. No, it is not easy to show it's not renormable. You can actually do calculations. Say, for example, 1 of 5 fancy process which we all need is Higgs to gamma process. That's how Higgs was discovered. Now, if you compute it in renormable range, it's not, people have computed in various ranges. Now, it's much easier, it also has a W. Okay? So it has to, the fermionic part is the dominantly the top part. You can compute it in unitary gauge, but it's prone to mistake. Okay, but other gauges, you can put it on computer and check it. You can cancel if it is Xi independence, you can show it clearly. So the renormalization is always typically done at one with using us. It's not that you cannot compute. Now, there are very famous people, I tell you a story later on. The Higgs to gamma gamma story, I tell you. After the Higgs story, in the next class when I discuss the quantum Lagrange. Yeah, this answers their question. Let's say what you want. Now, yeah.
T3 is hyperjumps plus this
Um,
SU2.
this one, the hypercharge. The hypercharge and electric charge are related by T3. That's why that. So this is your T3 is your third the labeling operator, just like in angular moment. So if you want, this is the SZ operator. SZ or
Half and minus half.
half and minus half essentially. And y is what you choose such that you fix your charges.
So here, so that so the upper component will is plus one.
Plus one electric charge. We are designing, we are doing noting the electric charge. It's a complex scalar part. It's complex scalar with charge. Now we will keep these things. There is something called the Goldstone equivalence there. Okay, I will come to it. It may be covered in the standard model course also, but independent of that, we cover. So the Goldstone independence theorem says that if we have any W, the longitudinal modes, wherever there is a Goldstone, you can put a W. Okay, we'll come to the quantum part later, but anyway, let's write the legend. Yeah, but this part is clear.
So I'm not what is T3 for A plus is
Okay, let's work out the T3 and charges, right, for example. So the upper part will always have half, and the lower part will always have minus half T3. Now the minus half, so y should be minus half such that the total charge of the lower part is 0, and it should be plus half such that,
it's one.
sorry,
It should be also
sorry, yeah.
Y should be then one.
Yeah, a y will be 1, yeah, or half, and depending upon, there is a freedom of normalization which I mentioned.
Okay.
Okay. So, yeah,
Yeah.
you want.
Yeah, that's right.
Okay. Is that fine? Now, this formula is very old. This formula came from the quantum. Okay, this is called Gell-Mann-Ricci-Jeevan formula. In that case, actually, instead of hypercharge, when it was incorporated into the standard model, they put in the hypercharge. But in that case, it's actually Bayer number, strangeness. So each quantum number for each generation is very different quantum. So just to keep the electric charges. Okay. So, but anyway, because we are going beyond the standard model, yeah. Yeah. Okay, any further questions? Okay, so we'll start writing the Lagrangian. Yeah. And then we'll try to discuss symmetries associated with each other. So, and fermions. I wrote kinetic for fermion. I don't know. Anyway, it's called kinetic. That's animals. Uh, if I use a different notation, I will use Higgs and scalar interchangeable. Now, what is this part? This part is the fermionic part. Gauge boson. This is the curve part, it's obvious. This is scalar. So this is spin half, spin one, spin two. So these are the particles which we have this time. There is only one spin zero particle, and there are a bunch of spin one particles, which are blue ones, W and Z. And spin half are all the matrix, which is also the matrix. So when we extend the random model, we'll ask, and we have other particles, other spins. There's also one more there. That's the reason why I'm insisting on this particular thing. Why can't we have spin two, spin particles? Spin 3 by 2. So L kinetic is nothing but for all the fermions are essentially QI, UI, EI. This is a very compact notation. This is your t-shirt notation. So that you can put it in t-shirt. Okay. So what it tells you is that all the fermions have a kinetic term, okay, which contains, we come to all the fermions here. Q means the left-handed doublet which we introduced for the quarks, right-handed doublet for the left-handed for uptype quarks, left-handed singlet for the downtype quarks, left-handed charge electrons, and singlet. We are not introducing right-handed electrons. So there are no right-handed electrons. And then what is this index? This is for each generation. I is equal to 1 to 3 is for each. So the first generation falls, second generation, third generation. Now here we have to specify what is D. D slash. So then among and then means now here I do one more compact notation. Okay. Okay. One IGS GU A. And here I put a delta such that it is only for quarks. Okay. I don't know, meaning I say this will be some delta, some F prime F Q, delta F U, delta F D. Okay, that means this is plus plus. So essentially, it's only non-zero for quarks. Okay. This is a terrible notation, but you don't have to follow it. Okay. Okay. I, G, weak, W mu I plus Ig prime y d. So instead of writing this table notation, we can skip this, but let's say that this only acts on quarks. All of them, Q, U, and D, all the three generations. And W, uh, this only acts on left-hand orbit. That means it only acts on Q and L. This is for everything else. Any questions? This notation, yeah. I want this notation to stick in your heads. Okay? Because anything we go beyond, I'll use this notation. Any questions on this? This is the blocks. There are eight. Eight is 1, 2, 3, 4, 8. This is a strong coupling. So what it means that I'm having a covariant derivative for all the three quarks. Okay? Participating in gluons with gluons. So it gives you a current interaction with gluons. Okay? And there are eight of them. Alright? The next term tells you that the left-handed parts, which are essentially this and this, will have a covariant derivative corresponding to W's. This is an unbroken phase. I'll tell you what happens in the broken phase. Okay? The W's and the Y will be for everything, all the five, six. Right?
What is the I index of the W?
I is equal to 1 and 3. This is not generations, but there are three. Okay, let me give you. Alpha is for three W's.
Which color?
No, no, these are W's SU2. SU2 gauge bosons. Okay. So this is SU3. This is SU2. This is V1. So what you do in gauge series is that for every gauge group you add a covariant derivative. Okay. For every gauge group you add a covariant derivative. So for the first we add gluon covariant derivative. For the left-handed particles, which are a doublet representation of SU2, we add a W representation covariant derivative corresponding to W's. Okay. And this is like QED. This is exactly like QED. Okay, the current interaction. Okay, let me just elaborate a little bit more.
Will the equation not contain the difference of the change?
Oh yes, I'm sorry. You are right. I was missing something. It does. It does. You're right. And these particles travel in. These are your Bellman matrices. These are your which are your sigma matrices. And yes, um, this is coming with something called adjoint. So you need to put in that agenda. Yeah. So let me just elaborate a little bit on this part. 1 second before coming to the symmetries.
G prime and Y both.
Yes. G prime and Y is the charge. Active charge. G prime is the coupling. Like a QED. So QD you put in the electric charge, but not QD because we work with electrons and protons. We don't put in one way. But if you work with quarks QD, you have to put the 2 by 2 or 1 by 2. Okay. Okay, let me just elaborate this part of the Lagrangian little bit. Uh, Here, so the first term, let's take quarks and gluons. So it gives me psi bar, so quark bar I d slash quark. Okay, the first term, and where I put d slash is only the current part. So quark I g s. Okay, and let me write explicitly del mu plus I g s lambda v g b a q. Now this is not sufficient to write the color indices also. Okay. Now this is the coupling. Now the point is this Q comes as a triplet. So there are three Qs here, and there are three Qs here. So I should put uh, alpha, beta, gamma, delta, I, J, K. Okay. So these are not generation indices. Okay. These are your color indices. Okay. There are three colors. I and J run. A is run from 1 to 8. A is run from 1 to 8. I and J run from 1 to 3. Three colors. Is this fine? Okay. Let's take this vertex a little bit more. The first part is just your Dirac kinetic term. Okay. Now, when I write this capital Q, it means both left-handed and right-handed transform the same. There is nothing which changes in the lambda rate. Okay. Nothing which it allows for all the possible things. Okay. So you have, if I write a vertex like this, the gluons are represented by this. So you have what I coming in, what j going out, and this vertex factor is minus I gs lambda ij with a, and the color index of this one would be ij bar of this particular gluon. So that you have to consider sorry j I bar I bar. Okay. Lambda ij, where q and q prime are sitting inside this. You both the q's are only left-handed. The same thing. If you think left makes it complicated, you just put u. The same thing also happens for u bar. Now this is not written in SU2 space. Remember, this is written in color space, SU3 space. This I and J are in color spaces. Okay, so imagine these. Okay, just write them the same for UL and DL. It's the same for UL and DL. You are the same. So these are in color spaces. There are multiple spaces in standard model. One is the Dirac Lorentz space, and of course, the color space. Okay. So the lambda is essentially your Gell-Mann matrix. G mu are K dot. Okay. Lambda I. This is your QCD, perturbative QCD. In particular, this is also called as perturbative QCD. Relevant for what energies it's relevant? Anything. So all the accelerators, colliders, except low energy colliders, something like Bell and Barber is not worth it. So things like LHC, Tevatron, left, in all these places, you have to do these calculations. You have to use perturbative UCD. UCD is weak, I mean, quote unquote, again, yesterday we talked about what is it's slightly weaker than the non-perturbative. Okay, this is fine. Right? QCD is fine. QCD is simpler. It is unbroken. This part will not change enough standard. Okay. This is unbroken. This these interactions keep happening. All you have to worry about when you disappear with the gluons. The gluons will become bound states. So let's come to the next one. The next one, again, this you must have seen in the course, but anyway, let's just consider only the QI. QI. For the present, I'll just forget about the mu. Okay, I'll only work about the interaction. So I G W mu tau A. Again, I'll put the indices I, J, and G. Now, what does this gives you? Again, remember tau. You all know your sigma max is very easy to write down. So it gives you two of them in the off diagonal. So there are two off diagonal entries. So what does it do? It takes, so if I take Q to be UL, DL, so you have W mu 1, 2, and 3. Okay, anyway, all of them, W mu, just forget about 1, 2, 3. You have UL going to DL, okay, with coupling, which is tau plus and tau minus, essentially, which is you can add the off diagonal entries, essentially, which I'll put it in brackets, tau plus minus. And there will be a third one. I'll put it the diagonal, which doesn't change the flavor. What it does, this one changes the flavor. Takes a uptype pop into a downtime. This is the one which is responsible for neutron decay, pion decay, everything. Okay, all the nuclear synthesis, everything is these are the ones. Okay. Any questions or comments? Yeah. Now the third one is your ordinary QCD, QED, exactly like QED, which is we can take any field essentially. So you are, let me call it as B mu instead of AB, which has a coupling. Ig prime. It is also diagonal. It doesn't change. It's also diagonal. All the fields. So we have written the kinetic terms for first part. This is obviously symmetric under the gauge symmetry. Obviously symmetric under the gauge symmetry. What are all the other symmetricities for? Kinetic part. So couple of things. Okay. Kinetic part, we assume it to be diagonal in the sense that there is no term which is multiplying. So you cannot have a kinetic term which multiplies different the initial part. So it contains two parts. Okay. So let's take the example of G again. The Q. Now this is always diagonal. You won't have any theories in which you have the electron the slash mu. Then you cannot build a proper quantum field theory. Okay. So what you do is this will only happen in certain cases when there is something called kinetic mixing. So you diagonalize, re-diagonalize them, you re-diagonalize them, and then express them PL and work with it because the kinetic term is important. Otherwise, we cannot build quantum field. Kinetic term should always be that. So the del P slash term should always be that. Otherwise, you cannot write an equation function. You do canonical quantization of mean anything. There are some theories in which the corrections could come, which are but then you re-diagnose it, and that's called kinetic mixing. This we'll see in the next one. It also happens in gate bosons. So the next one is Young-Mills. Use small a. This notation is better. I can use that a lot. This Young-Mills provides kinetic terms for gauge bosons. So kinetic terms, the gauge bosons also they're introduced when we define the symmetry, but they're also fields. So you have to also quantize them. They need to be having kinetic terms. Okay, so they need to have kinetic terms and the Young-Mills terms. So if you write a QD Lagrangian, it's not just write electron interaction. You should also write the Young-Mills terms. It's called Young-Mills for non-linear. The fields term is also there for photons. The first one, I'll just expand this. Now this is called something called structure constants, which you read. So the first term is like ordinary thing. Okay, the first term is like photons. Okay, so it just gives you the equation of motion for a photon. Okay, box G. But the second term, if I set Gs is equal to 0, it's like, but the second term depends on Gs. So that means you can have an interacting field theory only with gluons. Okay, you don't need matter. Okay, you can have an interacting theory if you have free gas of gluons is interacting. Now, if you take a gas of photons, for example, you start with Big Bang. Okay, you start with the gas of photons. So the gas of photons doesn't interact much unless you put in radio equations or annihilates and gives you some fermions or something. The interaction of photons with itself is very minimal. Does photons scatter with each other? Photons scatter with each other. Yes. And then there is something called the Dilbert scattering. You know about it. The Dilbert scattering is photon, 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 photon. Yeah. It's a complicated box diagram. And after doing this electrophysics, I started doing biology. Okay. After doing this box diagram. I was a student of board. Okay. Okay. So this is called Dilbert scattering. So you can have box diagrams. And this has been recently been used. Recent experiments. And it has some constraints. Say, for example, to modify gravity or something, this will have some constraints. In, instead of Euler Heisenberg, if you consider some other kind of thing, this nonlinear QD or any of these things will have constraints. So there are no constraints. Seems it can be measured at LSD also.
What about the terms arising from G mu and dual of G mu?
I'll come to that later. Okay, those are related to actions. They're essentially roughly zero.
Yeah.
Yeah, I'll come to that later.
Okay.
Right. Okay.
So how is that being measured this point?
Yeah, it seems they can measure it in. It's a complicated measurement, okay, but they can measure it in LSC. Ellis has papers on it. He was the one who did it again and computed. It's not easy because we also have initial state radiation, final state radiation. We have to take all those effects into consideration and then work it out what is the component of the initial state radiation. And with all these things, he says that you can isolate this signal.
So this thing with the dual part,
Right.
what part of the gravity does it give? Is it still like Young's?
Yeah, yes, it's a part of. So the question is that what happens with G mu, G mu tilde? Why only this term? What about W mu, W mu tilde?
They can
What about, okay, let's take even simple thing. What about H mu, H mu tilde? It's not big H mu tilde. What is thing? They violate something. What is some symmetry? Huh? Yes, they violate something. All of them are thinking violating. Okay, we'll come to that. Yeah, right. These they all come in kind of, but you need to put something in front of it, which is a pseudo-skeleton.
But essentially, they're all allowed terms in the Young.
In the Young case. Right. if you consider Maxwell's equation, for example, you need to consider this term also. Otherwise, you won't get all the four Maxwell. And if you have Higgs representation pseudoscalars, they come to this. But they will not be developed at tree level. They are not tree level, they develop in the physical energy. In the physical energy, high energy. Okay, for the present, let's not worry about it. I'll come to that later on, essentially. So the argument is only this, it doesn't have the duals. Okay. The reason is that you can set this term to 0, but then this gets generated by one loop, and then there are other loops. And it's a big story, I'll tell you later on when I deal with actions. And it's a very interesting story. Not even that. You cannot set it to 0 at all orders of freedom. That's the main result. Okay. Anyway, okay, now we have this thing. Um, unless we impose a symmetry, which is called the check symmetry. Uh, no, okay. So now this one, this part is an interactive. So free gas of, so if we have free gas of gluons, it's very strong. Now if we have, now if you produce a free gas of gluons, it doesn't stop. I mean, it starts getting from both states. Now, if you remember your plot model, you have a system of reducing the gluon states. You can have something called a elemental object called gluon. Yeah, you are remembering in nuclear important systems.
You can teach it, but
Yeah, but he must have mentioned it.
Yeah.
Yeah, a singlet which is fluorescent is called a gluon. We have not found evidence. We have some slight limitations, but it should be there and it's allowed by group three. Okay, you can have. So a free gas of gluons is completely opposite to the free gas of protons. That's what is surprising to me when people talk about quantum plasma. They don't actually fit it with a non-interacting gas. So, okay, okay. Sometimes it also fits. Actually. The data seems to be fitting. Anyway, okay. Now this, let's see the couplings. When you put back these couplings, because it has interactions, you allow triple and quartic gluon couplings essentially. This one is derivative, this is important for symbiotic freedom. Okay. And this is the quartic coupling of the gluons, which goes as higher order perturbation theory, which goes as ds square, this goes as ds. And you can see the explicit couplings and the calculation. One of the easiest books to look at it is Muta or Matthew. I think Schwartz is nice. Schwartz does the discussion very nicely. Now, this higher order in perturbation thing is not really surprising. If you take scalar PUD, you also have the same thing. So next is this number 4 W meaning, a W meaning I W W W. These also interacting. So this should I J A. So the I boson can be converted into J K boson. So basically, it interacts with W J and K bosons. Similarly, here an A boson, A gluon, can have components of B and C gluons essentially because of this. because of this thing. So you have A depending upon the structure constant. This is cyclic symmetry in something. There will be a minus sign and one plus sign. I don't remember the exact coupling constant, but I can dig it out actually. Okay. So this also is very similar. Instead of gluons, we have W bosons. These are extremely important. These are extremely important. Any deviations for this for test of new physics. Okay, we will see examples essentially for triple gauge bosons and 40 gauge bosons. These are actually test of new physics. Test of new physics. So any deviation from or any other gauge boson, I'll write them in broken phase later on. Okay, anything other than in Weltzman books, if you find a new complete, okay, that means it's a signal of new physics. Okay. So you'll find a lot of papers on this triple gauge boson. Policies. And why this is important is because we wrote down this particular thing in an effective theory, you have higher dimension operators. And these higher dimension operators for the gauge sector will modify these components. Nobody wants to touch QCD because QCD is nobody wants to touch it. But they want to, the moment you write a SM QCD, you will modify this. Any effective theory, you will modify this. Most of them. So the next one is the Yukawa. So from now we have the Higgs part only. There are three Yukawa matrices in standard. One for the octet quarks, yeah, I think it should. Why the Hermitian conjugate? Curve couplings can be complex. So the Lagrangian should always be real. Okay? So you add a Hermitian conjugate. And they are completely unconstrained random parameter. They are only determined by experiment. They are completely free. Okay? But they're determined by experiment and their determination is so constraining that we see that they have a very specific pattern. We have no idea why that specific pattern is. Okay? It's only completely determined by experiment. Now, what does this mean? If you expand this coupling, I just write EY into J at 0 DI. Oh, this should be tilde, sorry. It's minus. So let's look at one of these things. This gives you the mass for the particle. And with the same energy, there is a coupling with the Goldstone boson, which goes in this direction, which again shifts the flavor essentially. So the non-flavor diagonal part essentially is the one which gives you the mass. Okay. So this will I know because I contracted the SU2 indices of contracted this. How do you contract this into indices? It's like adding two doublets into a singlet representation, like your spin. Okay. In your spin, what you have down h plus h minus u. So you do take u h0 minus d h plus, and then you have the right hand part. This gives you the Dirac term for the mass, and this gives you the, the Higgs interaction. So this is the way you mean multiply this with this, multiply this with this, and that gives you this. The other simplest way of doing it is by contracting with antisymmetric representation. So this you take it as a vector VA, this you take it as a vector V. The antisymmetric combination of two spaces, two vectors, gives you the symmetry. The symmetry combination means you put instead of epsilon AB, you put a delta AB. Epsilon AB, you know what it is. Antisymmetric tensor of two dimensions. And if you want to get a triplet representation, you put a delta AB. That gives you a matrix. This gives you one term. Any questions?
Sir, these are all for left-handed.
This no, there is one right-handed part. This is the right-handed part. If I don't put Q, capitals are all left-handed part. The small letters are all right-handed. And if you don't put a right-handed particle, you won't get the mass. The mass is a kind of combination of left-handed and right-handed. So this is UL bar UR. I should put a bar here, but I'm too lazy to do it. Okay, it should be a bar. As such.
Is it possible to set h 0 to 0?
But
In the broken bit, is it possible to have h 0 and 0, which is
it's zero.
h 0 set to 0? So
It's zero set to zero. No, it's a constant. Otherwise, you won't get mass. We'll take these limits. We'll start with these when we see the symmetries. Just now, give me 1 second. What happens? Okay, so this is the same. This is the equal coupling which gives you masses, and there is a part which goes away because the H minus becomes Goldstone boson. So this will become G minus, and this goes to G. So in the end, the broken phase is just gives you mass actually, and the interactions with the Higgs boson, the physical Higgs boson.
In the Lagrangian, so there will be another for the mu1. No.
This contains everything. Mu1, tau, because I and J run for all the three generations. So these are 3 by 3 matrices. Okay.
No, I mean to separate the neutrinos from the.
Right? When you do that, the neutrinos will be, say for example, this part gives you masses only to the upside. This mass gives you masses to the downside. This gives you only to the charge. There is no term corresponding to this in the electronic sector, so that the neutrinos will not get emitted. So the neutrinos are always upside. So there is no term in that set. Okay, now let's come to the last part. Now these couplings. So these couplings are Ricard couplings. simulators. So you have U left, U right. This is what it is. Now, this can be in principle of that element in clear space. So this coupling is okay. And the last part, okay. Any questions on this part? Yeah. And the last part is the scalar sector, completely made up of only the Higgs part. We are stopping here again, dimension 4 terms. This is the mass of the Higgs. This is self-coupling. This is the mass of the Higgs. And this has a shape because it's completely scalar. Okay, this has a shape. This, I think you all know. So, spontaneous symmetry. So, yeah. Now we have seen all the 4 parts of the Lagrangian. Now let's plot what are they? All of them are invariant under SU2 plus U1. Do you all agree? Okay. That part you are sure. Right. But are there any other hidden symmetries in this Lagrangian other than this? Given the particle content and the directions, are there any other things? Now these symmetries are not automatic. Okay? Some of them are automatic. Starting with the easiest ones, which are. So again, today we'll deal with classical symmetries, which may or may not be valid at the quantum level. I'll tell you what they are. Yeah, as we see in the next lecture. So the first symmetry, other than the standard model, other than the gauge group, other than this, first one is baryon number. Standard model conserves baryon number. How do you show it? What is the baryon number of quarks? 1 by 3. Oh, fantastic. Okay. Then, so the kinetic part comes as q bar times q, so it is always conserved. Young doesn't have any baryon number. Do gluons have baryon number? No. Very good. Okay. And then Ikawa part, you see that they always come in this particular format. So baryon number is always constant. Okay. So if you take this to be minus 1 by 3, this will be plus 1 by 3. Doesn't distinguish between left and right. Okay. It's a global quantum number. So it's always constant. So this is U1. Very
Does it get broken from quantum level?
quantum. Normals. It's called. The classical level it's conserved. Sometimes people call it accidental symmetry. Now, lepton, I will call it as lepton numbers. The reason is we don't have neutrinos not having any mass in standard. We call it as lepton numbers. Because individually, Le, Lu, and then tau. For baryons, we cannot do that because the core matrices are Yij, both of them are present. So this point is clear. We have three individual lepton numbers because there is only one record, which is Lij. Now, what you can do is because you can always diagonalize this. You can always diagonalize this without any ambiguity in the Lagrange.
That is in the inherent gain of stars.
Nothing will change.
For electrons,
No, for leptons, there is no other mass matrix which has symmetry. So you can always have a rotation such that this always can be diagonalized. So So the kinetic terms and this can be simultaneously diagonalized. Okay. The reason is the kinetic terms are individual in L. This is kinetic terms separate for L and separate for E. Any rotation you can consider the kinetic term. The mismatch between this is the what matters. They won't appear in the kinetic terms. So the kinetic terms are L bar I del slash L and E bar I del slash. So you can always diagonalize simultaneously whatever happens. They can always be kept diagonal, and this always can be diagonalized.
so in case of you have two kinds of terms.
You have two terms, up sector and down sector. So if you rotate the Q, it will also rotate the other. So one field is constant in both the terms, in both the matrices. Okay, so you cannot, or one vector is constant. Whereas leptons you can always diagonalize. So you can treat each field of a lepton separately. Okay, and so individual lepton numbers can always be constant. At least at the T.
So what is the problem if we have a different number of values?
What is the probability?
What is the problem if we just impose a different number of values? Like observations just coming because of the differential capability, or is there reason?
Lepton number conservation is coming because of two things. One, the particle content as well as the terms which you. Now, the moment the problem is that if you want to add neutrino masses, uh, this won't hold true anymore. If you add a Dirac neutrino mass, if you add right-handed neutrinos, say for example, this won't hold true because right-handed neutrinos you can always add a Maranov. They are not constrained to any gauge limit. Left-handed neutrinos are constrained by the left-handed gauge limit. They participate in nuclear. Right-handed neutrinos, if you write the quantum numbers, the quantum numbers are 1, 1, 0. They're absolute singlets. Okay, so they don't have any other interaction. So you can always write a Maran master. If you don't want a Maran master, then you have to impose lepton number. The moment you write that introduce right-handed neutrinos into the standard model, lepton number is valid. If you want Dirac master, that's a problem. You have to impose that. Or you have a model in which those terms are not known somehow. That is the reason why theoretically you have new physics the moment you add neutrons. Otherwise, people can always argue that okay, and neutron just let an upset the mission. It doesn't happen that way. You have to add either new particles or new symmetries also. Symmetry arguments also. So these are also called center symmetries. They are anomalous. They're only valid at tree level. So that means the classical level. At the quantum level, the linear combinations are valid. So this is U1, LE, LE, and now. So there are four U1s. Instead of these four U1s, we have another ones which are valid at the quantum level. Um, Eta. These are non-anomalies. That means they don't lead to anomalies. I'll come. I don't know. I'll come to it at some point, but just remember that non-anomalous combinations are linear combinations. Anomalies are these are cubic anomalies. Okay, you have to work out the details. This is B minus L, LE minus LB, LB minus L tau, and E tau. Or LE minus L tau. So these are cubic equations which are like diquadrant equations, and we have to find solutions for it. And we can find solutions only for these linear equations. The anomaly cancellation equations. Okay.
I think you added the Newton. So will it violate the individual Newton number or the sum of the Newton?
Depends on how you value. Yeah. It violates the global authority. But you can be careful such that you conserve one of these things, one of these combinations. Okay. It violates definitely the global component. But there are models in which, for example, you can make models in which one of them could be always conserved because these are non-anomalous. And at some point, I'll come to something called long-range forces and stuff. Okay. These are very interesting stuff so that you can gauge them, and they'll be like QED, and they can lead to long-range forces. And if you and they can modify various things, like for example, corrections. Meaning, if there is a long-range force, you can compute the energy coming from the sun to the earth. Okay, and this will, and if there are nuclear emission from sun to earth, all these things can get known. And even if you have a very light gauge boson, you get impacted. Say, for example, you can charge dark matter in the new materials, and then have constraints coming from various things like the gauge boson is very light. You have dark boson. So if you have neutron stars filling, neutrons have a lot of muons, so they can attract a lot of this new dark matter candidates charged under these things. And then there are constraints coming from structure formation. Recently, there was structure formation. They are in gauge bosons. So these are very, very active field, lot of stuff. This is
So when you think D minus L, what L is
total electron.
sum of?
Yeah, L is equal. Now, these are the same thing, non-anomalous. These combinations are non-anomalous. That means even quantum corrections will keep them preserved. Okay? There are no anomalies. Now there are some symmetries which are not obviously evident. Which are obviously. Now these are symmetries which come by setting some terms to zero. Some terms. Okay. One of the first ones is called. You all know what is the scale transformation? What is the scale transformation?
Failure coordinates.
No. Okay. So if we have a scale, not ordinary exponent, essentially, if you multiply with the scale, it's scale transformation. Now, the scale transformation is violated in any theory which has a scale, which has any mass term. Now, in the standard model in the unbroken phase, what is the only mass term we have? Somebody answer. Doubt. X. Now, in the limit, X mass goes to 0. The standard model is scale. Okay? It's very interesting that mx equals to 0. There is a new symmetry in the standard. So you can always have scaling symmetries. Where do they come? Scaling symmetries, generator, you can write down scaling generator, scaling symmetry. In Poincare plus scaling symmetry plus special Poincare transformation is what? Conformal symmetry. So there is some theorem claiming that in 4 dimensions, scaling invariance is equal to conformal invariance. Okay. So in 4 dimensions, it is that scaling invariance is equal to conformal without having special conformal. So why we want to have a conformal standard model? That means it doesn't depend any scale. Standard model is there. Any energy scale. Beyond, of course, it's broken. We know that it's broken, but the reason is it can help you that it can help you with various things. Actually, people try to solve the hierarchy problem with it. Okay, they try to solve inflation essentially, where again scaling variance comes. Okay, if you want a Higgs inflation, you need a scaling variance. Okay, so in all these cases, you need scaling variance things. So they try to make it work. Now, this was first done by Barty. He's the son of the famous Barty. This is a different Barty. Okay. He's a Fermi lab. He's a particle physicist. The original Barty is a nuclear and chemist. He's a son of this guy is also very good. William Barty. And it's just a talk. Okay. But the idea that it's also useful. This limit, there are two things. One is scaling variance, but Coleman also used it for some other thing. So he wanted to dynamically generate Higgs mass. So he wanted to, because the Higgs couplings are what? Mu square and lambda 5/4. So if lambda 5/4 can generate the radiative correction, the Higgs mass, and make it negative, say for example, then you don't have to set this minus sign of the Higgs mass by hand. So what his idea was, he also considered this thing. This was in the 70s, and this was the beginning of the Coleman-Weinberg potential. So two things in the which one is scaling variance, the other one something called dimensional transmutation, in which a mass scale is generated by radiative. Okay? So you are creating mass dimensions by completely dimensionless theory. You have a theory which has no dimension. That means there is no dimensional parameter. But radiative corrections will generate a dimension. And it's starting with a we'll come back to it again when we discuss problems with spontaneous symmetry breaking. Okay, the basic problem in spontaneous symmetry breaking is that I'll also discuss it a bit later. That you have to fix your initial conditions. Imagine that we have a thermal bath of the universe, but it has to flow through this very finely tuned potential. So if it's such a finely tuned potential and the universe is flowing through that potential and only then there is spontaneous symmetry, means it's not natural, right? Some God is sitting there and making it roll it in this potential. Now, if you're against God, if you think that okay, everything should be more natural, this entire thing, the universe should automatically generate this kind of a potential, right? It should automatically generate. That's the basic idea of what Coleman has. That we have a thermal bond and we have radiative. At high energy, there is no symmetry. But then, as the energy decreases, meaning at the higher and higher, with radiative corrections, this term is generated and with a negative sign. The reason he thought it could be a negative sign because the fermionic loops can always make it negative. Okay? Now, turns out it's a very beautiful idea. It led to the entire calculation of fermion number. So the basic idea is that. So he called this idea that it's called dimension transfer. So he wanted to generate mu square by lambda with a negative sign with the Higgs boson. But it turns out the top part it doesn't work in standard. So if you set mu square is equal to 0, it does get generated at one loop, but the Higgs mass is 60 GeV or something, which is not what it is. So this doesn't work in standard. This entire idea. But it is useful for various other things. So we still have to live with naturalness problem. Okay. Yeah. And we have to still believe in God. Yeah.
Where does this dimensionlessness come from? Because there is no dimension in the
And the dimension. So the radiative correction will always introduce a scale. They introduce a scale with respect to the rest of the parameters, mass scales of particles.
so the relative corrections will depend upon the energy and
The radiative correction will depend upon what particles are in the potential. So that's the reason why he computed The relativity corrections to the potential.
So do you need massive particles or massless particles? Or
You need massive particles. They need to be high, yeah. Yes. They need fermions. And also the self-coupling of the lambda is also important. It also generates
with massless particles you cannot.
will not really completely work unless the top part is too heavy. So you need massive particles. All these particles. Even with purely massive particles, you have a connection to the um, let's switch up all the copper pins. And if you have 540, even in that there are connections to the from lambda by 4. Okay, where they're proportional either to the cutoff or the dimension scale at the scale of denomination. Because denomination will always introduce a scale.
So just from standard work, there is no way of saying what is the X.
No, there's no way we can. Higgs mass is an input. All the masses are input. Yeah. So global symmetry is Higgs. And the last one, uh, E is related to the sector of the curves. Okay. So we have scaling symmetry, U1 external symmetries, and everything. And then there is something called the flavor symmetry. So we put the Higgs mass to 0. Okay. And then we got this. We put the gauge boson mass to 0. You have the gauge symmetry restored. Okay, which is obvious essentially because there is no spontaneous symmetry. Now you can set Ecoff couplings to 0. Okay. You can set the Ecoff couplings to 0. So that means all the fermions are massless. Now, is there now any way of distinguishing electron with a muon? Understand? As far as we have engaged interaction, because of pins are 0, now you cannot distinguish electron with a muon or a tau.
What about the lepton numbers?
Electron numbers are always there.
I think if we have a muon,
Yeah.
then we can say that they should have been.
Yeah. Now, how do you distinguish them if they said, how do you distinguish electron? Muon is exactly like an electron with 100 times more mass. Now, the mass is 0. How will you distinguish?
So those neutrinos will be same.
Everything will be same. If the mass is 0, in the massless limit, when all the fermions are 0, you have a new symmetry called flavor symmetry. Means the weak interactions, anything, you can have spontaneously break symmetry. They won't distinguish between different flavors. So electron will be the same as muon, quark will be the same as this. So you can have a symmetry which up, down, what do you call it? Charm, they all can interchange themselves. They can transform as a triplet and it is U3. So if you converted U to C, C to P, and U to P, your Lagrangian is exactly the same in the massless form. So this is exactly like SU3 symmetry or SO3, but we have complex particles, so we call it as SO3. This is called SU3 for left U times you do the same thing for left right down Currently, the standard model has a huge symmetry in the limit of massless form. Completely. So how many? Is 2, 3, 4, 5. We are like in a nuclear physics class rather than okay. With lab, U3s and everything. But so, see that in the limit of massless form, standard model has simply power 5. In actual real case, it's actually U3 power 5, where U3 is U1 times x to 3, where U3 goes as U3, and this will correspond to the question of baryon number. So this is called flavor symmetry. So the Ecoff couplings will break this flavor symmetry. Okay. In the limit of the Ecoff couplings to 0, all the masses are same. So this is also one more hidden symmetry. Okay, one last. Give me 2 minutes. Okay, I'm sorry. Okay, just one more symmetry corresponding to this part. Very number. Left one.
It should also be baryon numbers, right? But
No, they are. You can write a U or you know that you can write upness, plainness, and stuff. They all are. So one last symmetry. You remember V of L for L of H. This is actually super symmetric. Okay, all kinds of symmetries you can. It's very hard to impose a symmetry which we know in the scalar set because scalar set always comes with the dagger and the hedge. So there is no unless you have supersymmetry, there is no symmetry in which you can constrain the scalar set. Okay, if you have a scalar part, it's very hard to construct a symmetry. Okay, especially the mark of this. Now this one has a symmetry. The standard model has a symmetry, which is real H plus imaginary. Now you can write them as 4 real fields, right? Essentially, because these are complex, every complex scalar field can be written in terms of 2 real scalar fields. So there are 4 real fields. So let me write it as phi 1. So when you write it down, this entire Lagrangian, this let me call it as phi tilde. This is just minus mu square phi tilde transpose phi. That's phi tilde phi tilde. This entire Lagrangian in this particular fashion, because it's real scalar fields, I'm putting a transpose. So this is SO4 symmetry. So this is SO4 symmetry. This has a very important thing, and you will see this plays a very big role in many cases, which is called custodian symmetry. So the standard model Higgs as a custodial state. Okay. Now you can ask the question: what happens if I add the kinetic terms of the Higgs sector? If the kinetic terms of the Higgs sector are even then this is preserved in a particular way. Even then, even then this is preserved in a very nice fashion. So this custodial symmetry conserves. It's very important that it conserves all the radiative corrections to the standard model gauge bosons. Because remember, three of them will go to be the Goldstone bosons. Okay, it's not evident if you start with the unbroken broken phase. In the unbroken phase, you can see that three of them will end up being the Goldstone bosons, gauge fields. So all the radiative corrections, especially to the masses and the widths of the gauge bosons, are related to this symmetry. Okay, so these are hidden symmetries as far as I can tell. Okay, right. Okay, of the standard model. Okay. And next class we will do um, the quantum mechanics. We'll see the radiative corrections. Any questions?
So these over symmetry.
This also can be written as SU2 times SU2 sometimes. People write. Yeah.
So while solving the hydrogen atom problem, so someone solves this symmetry and can get the energy.
And hydrogen atom is more related to the angular momentum. So the angular momentum, and there is one more Lulj.
Exactly.
Yeah.
A equal to R.
Now here this is more related to the interacting currents. Therefore, what happens is that J mu in a way, because it's all SU2, right? In a way, it is somewhat connected to that essentially because there also it's SU2, here also it's SU2. So there's an extra SU2 in hydrogen atom. So that SU2 and there's the SU2 of the normal isotopy SU2, but there's an extra SU2. That's the basic idea. Essentially. Okay. Okay, but I don't know if you can directly relate to each other. But what happens is, in this case, you can write the currents, get W currents, and you can show these currents satisfy a particular relation. They also form a triplet under this issue. Obviously, it's obvious, right? Because the gauge boson transforms in triplets, so the currents also should, and they satisfy this issue. And they have a relation between the currents in the broken phase, and that's the reason how they conserve all the pies. Pies are your self interaction. What do you call it? Yeah. Okay, these are memories. Okay. Self memories. We conserve all this. And this is how they rolled out technical. So when technicolor was rolled out, this created a metro issue. So we'll come to that.
What is the JMU W?
Uh, G is this if you look at it in terms of the current interaction terms, actually it has Higgs with W boson, right? That's what is the current. So every interaction can be current term. Okay. The Higgs boson has interactions also with the W bosons. So if it has some right, that's the right J. So every vertex is considered as a current interaction.
How is it related to the time?
good question. But so this is the current. Now, this is also correct. Now, these are Boston bosons here. They could be Boston boson components of the field. Now, if you have extra particles okay, other than these will modify, these will appear in measurements of these widths and masses of these gauge bosons. For example, pi medium will appear in the explicit expression. In the say for example, there are four pi mediums: gamma, 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 z, gamma, z, z, and w. The linear combinations of them will correspond to will appear in the widths of the various what do you call say Z boson. What are the things which are measured? But I'll just give you the measured ones are essentially the width of the Z boson, mass of the Z boson. These are very well measured. Science related. So these things now, now if you write in a renormalized energy, this will contain the pies dependent on this. So you can isolate the pies.
So these are self-energy diagrams.
These are self-energy diagrams of the gauge bosons. It's exactly like pi gamma.
And this Boson bosons will also continue.
Of course, they must. Why they are, meaning they cannot be, why they are what they are essentially is this, anything which is strongly interacting with Higgs is not allowed purely because if you have a colored particle, extra colored particle, will not be allowed because it can modify these things very strongly. And because they break the custodian symmetry. They break the custodian symmetry. So anything which breaks the custodian symmetry, I will tell you why they are related. The custodian symmetry and itself. So if anything which breaks the custodian symmetry will break this Christian measurements. Okay? By a large margin. And that's how you can rule out that particular theory. So custodial, any new construction should not break any of the symmetries which I mentioned. Yeah. So all these symmetries are essentially just an organizing principle. You have all these symmetries of standard, and they are also sort of protecting standard. Okay? Very strongly, they are protecting standard. So if you want to tamper it, you have to tamper it very carefully. Okay. Right. Yeah, and from the next class we'll start looking at one root renormalization. I want to tell you various again each sector we look into it greater detail and see what happens. Yeah, someone wanted exams and assignments. Who was it? Just give me your names essentially. Yeah.
What is it physically?
Uh, okay.